Hello Chem 1A, this is Chapter 11, Lecture Video 5, and we're going to be discussing molecular polarity. This is distinctly different from our last lecture video where we talked about bond polarity. Now, in order for an overall molecule to be polar, it must have two things. One, it has to have at least a single or more polar bond in the structure. And two, it actually also depends on the molecular shape of the compound. Specifically, the more symmetrical, the more non-polar the molecule is. So even with polar bonds, if the molecule is exceptionally symmetrical, then it still is most likely going to be a non-polar molecule. The less symmetrical means the more polar it is. Now, this is under the assumption that we have at least a single polar covalent bond within the molecule. So this can be shown in these 5 molecules below. And if we look at these 5 different molecules, each one, what we're doing is we're adding a chlorine each time as we go from left to right. So on the very far left, we have a CH molecule. Then we have CH3Cl. So we got rid of one hydrogen, we add a Cl. And then this continues as we go all the way until the end, until we have 4 Cls all around our carbon. Now, this is great, but the first thing we have to understand is that in order for a molecule to be polar, it must have a polar covalent bond. And one of the things we talked about is that CH bonds, what we have here, right, are not polar. So there are no, I should say no polar bonds in this molecule. This means this molecule is a non-polar molecule by default. Now, as soon as we add a Cl, though, in replacing it with a hydrogen, or replace a hydrogen with a Cl, sorry, we do absolutely have a polar covalent bond. This is a polar covalent bond between the carbon and the chlorine. And what we see is that because chlorine is so electronegative, it's going to start pulling electrons towards itself. This is going to cause a net, what we call a dipole moment, which is an uneven distribution of electrons across the molecule. And it's a permanent one. It stays there because of chlorine's high electronegativity. This is a polar covalent bond. And if we look at the structure here, it's not super symmetrical. We have the chlorine on top and we have all these Cl's down below. There's no chlorines down below. This molecule is not very symmetrical, and therefore it has a net dipole moment, or in other words, this molecule is polar. And you can kind of see the net dipole moment here as a value. We don't really need to worry about values here. It's going to be kind of useful in our discussion on this slide as we get to the next one and the one after that to talk about which one's the most polar. It turns out that CH3Cl is the most polar of the molecules on this slide, and we'll talk about why in a second. So let's talk about our next molecule. Our next molecule is CH2Cl2. Now in this molecule, we have 2 polar covalent bonds, one here and one here. Both the carbon-chlorine bonds are polar covalent bonds. And because of this, we have dipole moments of electrons getting pulled towards each one of those chlorine atoms. Now what that leads to is a net dipole moment across the molecule going this way. It's still a very polar molecule. It's not perfectly symmetrical. We have chlorines on one side, we have hydrogens on the other. And so with its polar bonds and its asymmetry, we have a polar molecule again. So this is still a polar molecule. But because these 2 chlorines are now present, both of them are kind of fighting to pull electrons towards themselves, and they cancel each other out just a little bit. And we can see this in the value of the dipole moment. You can see it's slightly smaller than our CH3Cl. They're both still very, very polar molecules, but technically CH2Cl2 would be probably slightly less polar just due to the there is a little bit more symmetry here with the second chlorine. Now, if we look at the next molecule, we have CHCl3, and now we have 3 polar covalent bonds. All the carbon-chlorine bonds are polar covalent bonds, and absolutely all of them are pulling electrons towards the chlorine because it's the more electronegative element. And this leads to an overall net dipole moment of electrons being pulled towards this side of the molecule. Now, this molecule is still not super perfectly symmetrical. It's going to be polar as well. It's actually the least polar of the molecules that have been polar so far, with a dipole moment of 1.04. Again, the numbers aren't very important, just in that we can kind of see how adding the extra chlorine actually kind of takes away from the pull of the other chlorines, because now they're kind of fighting each other for electrons. This decreases the polarity a little bit. Still, we definitely call this molecule very polar. This brings us to our kind of extreme, where now every single bond is a carbon-chlorine bond. All of these bonds are polar covalent bonds, but because of how symmetrical this molecule is, they're all pulling electrons towards themselves. But because of the symmetry here, all of these electron pulls that these chlorines are doing are canceling each other out, and we end up having no net dipole moment. So because of how symmetrical this is, even though we have polar covalent bonds, it's a non-polar molecule. Just as a reminder, there are really 2 major types of non-polar covalent bonds, and that is where we have an element bonded to itself. So any element that's bonded to itself would not be a polar covalent bond. And this is also true whether we have a single bond or a double bond. If you have double bonds, that doesn't affect polarity, or triple bonds don't affect polarity. It's just the element's electronegativity that affects polarity. And then the other option that you really should know about is the CH bond. CH bond is a non-polar covalent bond. These are really the 3 possible, or the 2 possibilities, is where you have an element bound to itself. That's a non-polar bond. And when carbon is bound to hydrogen, it's also a non-polar bond.
So the first one, like I was saying, is you should ask yourself basically a couple questions here. One of them is, does the molecule have polar bonds? And if the answer to that question is yes, then it might be polar. It might not be polar. We don't know. That's not enough information. It might not be polar. We don't know. Could go either way. If the answer is no, then the answer is it's nonpolar. And we're done. That's a nonpolar molecule. If it does not have any polar bonds, by default, it's a nonpolar molecule. And the second question you should ask yourself is, great, we have a polar covalent bond. Let's move on. The second question is, you should ask is, are all the terminal atoms around the central atom the same? I guess the same element is what we really care about here. And if the answer to this question is yes, then again, it might or might not be polar. Still don't really know. If the answer here is no, it's polar. The third and final question here you need to ask is, are there lone pairs on the central atom? So if that question, the answer is yes, then it's polar. And there are two exceptions to this statement. We'll talk about them. If the answer to that question was no, then it's a nonpolar molecule. So what are the two exceptions? The two exceptions are when we have specific molecular structures that are very, very symmetrical, and therefore, even with the lone pairs on the central atom, it's super symmetrical, so we have a nonpolar molecule. And they are when your electron group geometry is trigonal, bipyramidal, and your molecular geometry is linear. As you might imagine, a linear molecule, if the two elements around the central atom are the same element, it's an incredibly symmetrical molecule, but in this structure we actually have three lone pairs. This is still a nonpolar molecule. The other exception is when your electron group geometry is octahedral and your molecular geometry is square planar. In this structure, you have two lone pairs. But as you might imagine, it is an incredibly symmetrical structure as long as all the elements, the terminal elements, are the same element. So these are the only two exceptions. So if you have one of these two, then it's still a nonpolar molecule even though you have lone pairs. But otherwise, all other molecules, if there's lone pairs on the central atom, they're going to be polar. And so hopefully this helps you kind of figure out whether a molecule is polar or not. You really just need to ask these three questions about the molecule. And so let's try practicing it a little bit on the next couple slides.
Okay, so let's do some practice problems. Let's use those rules we just learned to kind of figure out whether these molecules here are polar or non-polar. All right, so first we have to draw the Lewis structure. That's always the first step. So if we draw the Lewis structure of CO2, we get a structure like this. Now, if we go through our list of rules, the first rule, or the first question we're supposed to ask is, are there polar covalent bonds in the structure? And the answer to this is absolutely with carbon dioxide. Carbon-oxygen bond is definitely a polar covalent bond. So yes, there. That means it might be polar, it might not be polar, it depends. Right? Now these guidelines are really just helpful. If we actually just look at the structure, we can see it's super symmetrical. Most likely this is going to end up being a non-polar molecule. Let's go to our next question, right? Which is, are the elements around the central atom the same? And that is also true, right? We have an oxygen here, we have an oxygen here, they're the same element. So yes, these elements are the same. This brings us to our last question. Are there lone pairs on the central atom? And the answer is no, which leads us to this molecule being nonpolar. If we draw the Lewis structure of water, all right, kind of looks like this. First question, are there polar covalent bonds? Absolutely. The oxygen-hydrogen bond is definitely a polar covalent bond. Are all the elements around oxygen the same element? Yes, they're both hydrogens. And then finally, we get to our last question. Are there lone pairs on the central atom? Well, yes, obviously we can see there are actually two lone pairs on the central atom. So this molecule is definitely polar. Okay, so let's draw XeCl4, right? So if we draw XeCl4's structure, it looks something like this. And we have 2 lone pairs on the central atom. All right, so this is, does it have polar covalent bonds? Absolutely. The XeF bond is definitely a polar covalent bond. Are all the elements around the central atom the same? Yes, definitely. Are there lone pairs on the central atom? Yes. Now, this is where our guidelines tell us that this should be then a polar molecule. But if we know our geometries, we know this molecule is electron group geometry octahedral, molecular geometry square planar, and because of that, we know that's an exception to our guidelines because this molecule is exceptionally symmetrical. This is a nonpolar molecule. If we draw CH4, we get a Lewis structure that looks like this. Now, this Lewis structure tells me that I have polar covalent bonds because the CF bond is definitely a polar covalent bond. All the elements around the central atom are the same, and we have no lone pairs on my central atom, so this molecule is non-polar according to our guidelines. And that's accurate. Now, if we draw our last structure, SF4, we get a structure that looks like this. And this structure has polar covalent bonds. The SF bond is definitely polar. All the elements around sulfur are the same. We have fluorines all the way around. And we do have a lone pair. This tells me, according to those 3 questions we talked about, this is a polar molecule. It's definitely not one of the exceptions being square planar, Mg, molecular geometry, and linear with trigonal bipyramidal electron group geometry. And it's neither of those. This is a trigonal bipyramidal electron group geometry, but a seesaw. And so this is a polar molecule. All right, so if you guys have any questions, please don't hesitate to ask me. I'm always happy to meet with you one-on-one or in my office hours or via email alone.